Welcome to FrontEndSystemsLab. This is a channel where we explore what's going on under the hood of modern web development. On this episode, we explore local AI GPU systems. Come along as we go under the hood of the modern inference. Most people think running AI locally means installing a model and chatting with it. That idea is incomplete. A local AI system is a tightly constrained inference pipeline built around GPU memory limits, bandwidth ceilings, and optimized matrix execution. The model is only one part of the system. The real behavior comes from how data moves through hardware. A GPU is not a general-purpose processor. It is a parallel matrix engine. It is designed to execute thousands of identical operations at the same time. This structure matches transformer models almost perfectly. Transformers are built on linear algebra. They rely on repeated matrix multiplication, attention scoring, and vector transformation. The GPU does not understand language. It executes numerical operations at scale. Modern GPUs such as the RTX 4090 or data center A100 class hardware are built around different memory architectures. The 4090 uses GDDR6X memory with extremely high bandwidth. The A100 uses HBM2E memory designed for sustained throughput. This distinction matters more than raw compute. Inference is not limited by flops in most real workloads. It is limited by how fast data can move through memory. Every local AI workflow begins with model loading. The model is stored on disk as quantized weights. These weights are moved from SSD into system RAM, and then into VRAM. This transfer path is critical. SSD speed affects startup time. PCIe bandwidth affects staging speed. VRAM capacity determines whether the model can actually run efficiently. If a model exceeds VRAM, the system begins offloading to system memory. That immediately reduces performance by an order of magnitude. Once the model is inside VRAM, inference begins. The input prompt is first tokenized. Tokenization converts text into numerical IDs. The GPU never processes language directly. It processes tokens. These tokens are then converted into embeddings. Embeddings are high-dimensional vectors that represent semantic relationships in mathematical form. The first major computation stage is the prefill phase. This is where the model processes the entire input context at once. The transformer builds attention relationships between all tokens. This stage is computationally expensive because attention scales with the square of sequence length. Longer prompts increase workload exponentially. This is why long context models require significantly more VRAM and memory bandwidth. After prefill, the system enters the decode phase. This is the steady-state generation loop. The model generates one token at a time. Each new token requires a full forward pass through the network. It also requires reading and updating the KV cache. The KV cache stores previous attention states, so the model does not recompute everything from scratch. This cache grows as the conversation length increases. It becomes a major consumer of VRAM over time. Performance in this phase is measured in tokens per second. This is the most practical metric for local AI systems. A consumer GPU like an RTX 3060 can achieve around 10 to 25 tokens per second on small quantized models. An RTX 4090 can reach 60 to 120 tokens per second depending on model size and optimization. These numbers are not theoretical. They are constrained by memory bandwidth and kernel efficiency, not just compute power. Quantization is the primary reason local AI is possible on consumer hardware. Models are typically trained in FP16 or FP32 precision. That level of precision is not required for inference. Quantization reduces weight precision to INT8 or 4-bit formats. This compresses memory usage and increases throughput. The trade-off is numerical precision loss. In practice, transformer models tolerate this well because they are overparameterized during inference. Different quantization methods produce different results. INT8 maintains higher accuracy but uses more memory. 4-bit quantization allows large models to fit into consumer GPUs, but introduces more approximation error. Modern methods such as AWQ and GPTQ improve quality by optimizing how weights are compressed. This allows larger models to run locally without catastrophic performance loss. Software frameworks control how efficiently the GPU is used. CUDA provides the low-level execution layer for NVIDIA hardware. TensorRT optimizes inference graphs for maximum throughput. VLLM improves batching and KV cache management for transformer models. Llama CPP enables highly efficient CPU and GPU hybrid execution for quantized models. Llama provides a simplified runtime layer for local deployment. Each layer reduces overhead and improves hardware utilization. Memory bandwidth remains the dominant constraint in almost all local AI systems. Even if compute capacity is available, the GPU cannot process data faster than it can be fed from memory. This is why architectures like HBM in data center GPUs outperform consumer GDDR in sustained workloads. Bandwidth determines how quickly attention layers can access weights and cache data. It directly controls generation speed. The system bottleneck in local AI is rarely the CPU. The CPU handles orchestration, tokenization, and input processing. Its role is important but limited. The real performance ceiling is determined by VRAM capacity and memory throughput. Once those limits are reached, scaling the system requires either quantization, model reduction, or multi-GPU parallelism. Multi-GPU setups introduce additional complexity. Tensor parallelism splits model layers across multiple GPUs. This allows larger models to run, but introduces communication overhead between devices. NVLink reduces this overhead in workstation and data center systems. Without high-speed interconnects, multi-GPU scaling is limited by PCIe bandwidth. Real-world local AI systems fall into predictable tiers. Entry-level systems use mid-range GPUs like the RTX 3060 and run 7B parameter models in quantized form. Mid-range systems built around RTX 4090 hardware can comfortably run 7B to 14B models at high speed and handle some larger models with optimization. High-end workstation systems use multiple GPUs or data center hardware to run 30B to 70B models with acceptable latency. Model choice also affects output quality more than most people expect. Smaller models with good quantization and optimized inference engines can outperform larger, poorly configured models. Architecture matters. Attention efficiency, grouping strategies, and kernel optimization often have more impact than raw parameter count. The final mental model for local AI is not software-based, it is systems-based. A prompt enters the system as text. It becomes tokens. Tokens become vectors. Vectors become matrix operations. Those operations execute inside GPU memory under strict bandwidth constraints. The output is generated one token at a time through a probabilistic sampling loop. Local AI is not a chatbot running on hardware. It is a real-time numerical pipeline shaped by physical constraints. Once you understand that, every performance difference becomes predictable. Every optimization has a clear purpose. Every hardware decision becomes a trade-off between memory bandwidth and compute balance.